Good afternoon, everyone. Let me start right away with maybe the key message that I wanted to get across. And that is that I think we have to think much more about how quantum computation could really work in a more end-to-end setting. And with that, I mean heterogeneous compute. We heard some of this before, how hardware could relate, and GPU and CPU and QPU, etc. But I mean it more from an application perspective. How do we start to think if we have any form of application when we want to decompose it into a CPU and we want to have a GPU in the background running as well? How do we want to deal with data, for example, laboratory data? Where do we include that in the process? How do we run this when we start to think about real hardware and think about constraints of noise, etc.? How do we manage that whole thing from an application perspective? So that is what I wanted to talk to you about. And the reason why I want to talk to you about this is that I think this is not easy. It's really not trivial to think about, once I have an algorithm, how do I really start to use this in practice, and how does it really start to make a difference? There really is a lot of different domain knowledge that is necessary to think about the chemistry, for example, to think about the domain knowledge in, when you think about batteries or drugs or about catalysts. There you have so much to know about how these molecules and materials work that it goes far beyond just algorithms. And I want to take you on a journey to see how we can get that to work. I didn't just want to challenge to think about this. I also wanted to show our vision of how we could do that. And we call that quantum-centric, data-driven R&D. A bit of a mouthful, perhaps, but it's maybe a bit of a combination of quantum-centric supercomputing, combining some of the ideas we heard earlier today, for example, from quantum machines about how you can have this heterogeneous compute, but also with data-driven R&D. Maybe a big part of the bread and butter of my company to do data science and to do R&D based on data. And so why am I here? Let me take maybe one step back. Is that I am from Capgemini, which is a technology company that does a whole range of things. We do things like engineering services. We do things like AI modeling and creating big AI models. And we work side by side with many of our companies to do things like R&D, for example, in the pharmaceutical space or chemistry or whatever. And the goal of what my team is here to do, we are basically a group of physicists, is to really show the path how can we get to applied quantum advantage, and not just to show this path, how this might look like, but also really to build along the way and make sure we get us there. Overall, we are more of an R&D company than a quantum company. Capgemini is massive, about 300,000 people. Unfortunately, my team is not that size yet. Which has some advantages as well. Because we're more of an R&D than a quantum company, we have a long-term vision, and we can be really honest about what the future of quantum could look like. And maybe, of course, one of the most honest things we should all start with is that, true quantum advantage is probably many, many years away. Quantum computers, of course, are notoriously difficult. They're noisy. They're small in scale. They're very slow. I think anything we've seen so far is just basically toy problems and doesn't get us too far. I think quadratic algorithms are quite in trouble. I don't see there's too much value maybe in the next decade in those type of applications and many of the industries that relate to that. But there are also niche applications and things that might be happening much sooner. And I think that the killer application that started perhaps this whole field 30 years ago, 40 years ago, is still there. And quantum chemistry and material science is still one of the key things that we hope to achieve. And I think we should not underestimate how important this is, right? It is important for our automotive companies that want to develop hydrogen fuel cells, for climate tech, for drug discovery, and for many other areas. So we know that for many of these problems that there is a very perhaps intuitive reason to think that quantum computers could speed things up here. Right, we know this from intuition, and perhaps it's best exemplified by the very famous quote from Feynman that nature is quantum mechanical, damn it, so we better need something quantum mechanical to simulate nature. But we also know this from experience, right? Many of our clients are using massive HPC center to simulate the behavior of some of these applications on the screen. We know that machine learning is increasing in size. The latest models are extremely big and so are extremely difficult to work with. And so we have really a good indication or a good hope that in some of these challenges, especially where we perhaps see things like strong correlations, we might have a hope that there could be a quantum advantage. Now, I think it's fair to say that AI is increasingly powerful, and it can do a lot of the things that we want to do in this field. I didn't hear anyone say so far talk about ChatGPT, and in our company everyone talks about it. So let me just get that out of the way and mention it. And I think it's for a good reason, right? I mean, these new AI tools are so powerful; they can do amazing things. And it's really something that we cannot get around with. It's much more important to start thinking about how we can build our models in collaboration or in connection with these kind of tools, instead of trying to beat things like perhaps protein folding, which I think is an excellent example where AI really proves that it could do things that we previously thought would not be possible. And so what I want to share with you is to think about how can we really create them, connect them. How can we build an application where we use classical compute, where compute is cheap, where we use AI, where data is cheap, and where we use quantum, well, basically where everything else is very difficult, and bring those three together. So if we think about what are some of the requirements that if we really want to have this end-to-end approach, I think the first thing is, we mentioned earlier, we need this heterogeneous compute. We need to think about how we can combine hardware, GPUs, CPUs, QPUs, etc. But not just from a hardware level, also we need to think about how can we decompose our problems, how can we think about fragments of molecules instead of the whole molecule. We need to get the most out of hardware, obviously, and we heard things about error mitigation and error correction before. But we also need to think about how can we really specialize the quantum computer at the core where it's most needed. For example, because we see strong correlations and we cannot, it's very difficult to address those with a classical computer. And we also don't have any data, and so the only option that we have left is a quantum computer. And third, really, if we really start to think about how can we get quantum to work as soon as possible, but we also just sort of see that as an intermediate step to larger applications in the years to come, how can we build a roadmap towards something that increasingly adds value? And so how do we create a pipeline that adds flexibility and that adds scalability into it? So scalability in the algorithms that you use, in the hardware that you use, and so really how you do not get vendor locked. And so the vision that I wanted to share to you today, that we have been working on in the past few years, is this technology that tries to address this. So this quantum-centric, data-driven approach to R&D. And so really this is a framework that we have worked on and we have tested and validated with very good results with some of our clients. And it starts with thinking about what are really the problems that could generally benefit from a quantum approach. Where do we, for example, see strong correlations, or where do we see some interesting chemistry that we know we would not be able to address? A second stage could be how can we pull that apart? How can we use perhaps a quantum solver for maybe the protein that binds to part of the medicine that binds to a protein, because we know there's very interesting chemistry going on, and we solve that with a quantum processor. And how can we model the environment with some of the other classical solvers? And then really, how do we find these active spaces that we want to simulate? And I want to say that this is not trivial, right? I think this is not so much covered here in this conference so far. But really, if we want to use quantum algorithms and apply them in real situations, we really need the help of chemists and of domain experts to think about where really are the most toughest problems. If we go to the second step, it's really about how can we get information out of those molecules or materials that are perhaps informative for the tasks that we have at hand. So how can we extract features from our molecules and use them in a data-driven pipeline to predict things like perhaps efficiency of a photo panel, or perhaps reactivity of some drug, or perhaps toxicity, all kinds of things that we would want to predict, but that we need to get the quantum data or behavior as a feature in the learning process. And this feature extraction, so we can, of course, do many things, many different algorithms. We can think about ground states, but there can be perhaps much more interesting things than just looking at ground state energy. We can think about some time evolution. We can think about things that are really physics informed because we know that there's interesting chemistry going on. We can also think about how can we think about maybe hardware efficient unitaries that we can map efficiently to the quantum computer and therefore make it much more available to near-term hardware. Or perhaps we could even think about, can we get features that are in itself data-driven, that are parameterized and that we can optimize so that they are as most efficient and predictive and informative into our machine learning pipeline. So if I go to the next step in our machine learning, in our quantum-centric data-driven R&D, it's really about using that very rich data sets that we have created with these quantum fingerprints, these very characteristic features of our molecules and the materials, and what kind of data analysis can we start doing with them. And so one thing could, for example, be to predict toxicity or to predict efficiency. But you can imagine there's a whole range of interesting machine learning tasks that we could do once we really have a powerful data set. And I wanted to mention that none of these, or many of these steps are done before by many different groups, right? There are groups that are studying embedding, there are groups that are studying different types of quantum algorithms, there's many groups that are studying machine learning. But when you bring those together and when you start thinking about this end-to-end pipeline, I think that's really where a lot of value comes from. Because then you can really start to think, what kind of simulations, how can I have real applications, real molecules? How can I get real data out of them? And how can I get real informative decisions with machine learning? So if I go to the next slide, I wanted to show a bit more how this could look like. These are just a collection of a bunch of work we did with various companies. And the first one is really to show, we take a molecule and we split it up into different parts where we study parts of the molecule with a quantum solver, whatever it is, and then model the environment and the bath in the environment with different tools. The next step would be then to extract quantum features from this. And in this case, there should be a video, but you should be seeing, or maybe it was, that there was, gave a kick to this electron and then measured how it evolved over time. And they showed to be very informative into our machine learning pipeline. Right, and so I think it's very interesting not to limit ourselves to just, just a quantum algorithm, just a QOA or whatever that predicts something of this molecule, but really to optimize this so that we can use this, get as much as possible information out of our systems that we can use in a machine learning pipeline. And then third, what you see here in this example is to see once we have this very powerful data set, this data set that has this very characteristics or these fingerprints of our molecules, what kind of machine learning or what kind of data analysis can we do with this? In this case, there is a classification algorithm, and so you can see that these fingerprints, they are showing very characteristics behavior of different molecules. We can cluster them, and we can therefore predict some of the behavior. We could also do direct regression or prediction, and for example, predict toxicity. Or maybe we could even think about doing things like generative AI, having a fingerprint of some molecule and then going back to predict what kind of molecules would fit that fingerprint. So I wanted to bring these different components together. So we have an end-to-end pipeline where I think many of these things are being studied, but what we really try to do is bring them all together and use them for real molecules. And with very good results, because we can really see that, even of course, though quantum advantage is still quite a few years away, this is something where we can build a scalable path and increasingly add more complex features to our machine learning to simulate molecules. There will be tomorrow one talk by my colleague, Sam, in the front here, that will apply this to a particular case, which is about the predicting reactivity of covalent drugs using these quantum computed features. So I wanted to close off by saying that I think we have some very exciting results in this type of work, which is a quite general framework to combine different type of quantum and classical solvers. But there's so much more work to do, right? And I think that using this in practice is not easy. We see that that the gap is pretty much widening between what is available and what can really disrupt. And I want to challenge you all to think about with us how we can not just think about one algorithm, one version of QA, or one version of phase estimation or whatever, but really start thinking about how can we use this in real life applications when we couple it with machine learning and when we couple it with other solvers through appropriate embeddings and then make it to work. So with that, I would like to call for that collaboration, and thank you all very much for your time.
Thank you very much, Julian. I think we have time for a few questions. So yeah, feel free to ask a few questions to Julian. Just raise your hand. There is a hand. So can we bring the microphone?
Julian, thank you very much. You mentioned about this quantum fingerprints, right? It's very interesting. Do you have any validation with respect to the classical fingerprints that we normally use? Do you have how orthogonal are they, and how big? I mean, what is the limitation of the size of molecule you can extract the fingerprints from with the quantum nature?
So by using these embedding technology, we can of course capture quantum behavior at a smaller scale than would be possible without using embeddings. At this stage, of course, the scope of what you can do with quantum algorithms is very limited. But as that grows, we'll be able to simulate larger fragments within larger molecules. And then the idea, of course, is that you'll be able to capture interesting chemistry that you would not be able to capture with just classical algorithms, right? Because you really look at chemistry that is beyond the reach of classical algorithms. And now the next question is how informative or how important is that part of the fingerprint for your decisions? And we have had some early results with, for example, in drug discovery to show that this is indeed the case, that this is something where you can very clearly predict, for example, toxicity. And for more details, I would also like to refer you to Sam's talk tomorrow that really goes in depth in this particular case.